you. So, hello everyone. I'm Pedro from the University of Porto. And I'm going to talk to you about an interpreter, a lightweight interpreter that we developed for teaching functional programming. So this is joint work with Rodrigo Marques, who's also there. And so let's start with a bit of context. So we teach functional programming as a first-year course. It's not the first programming course they have, but it's a first-year course. And it's a standard curriculum, so evaluation by rewriting, recursion, data types, higher-order functions, etc. And I found about a year and a half ago that I really wanted a lightweight tool that could be used to show that the computational model of functional programming, so show equational reasoning where each step in your computation is justified by one of your program equations. In this style, the style of the textbooks by Bird, Wadler, etc. I wanted this to be web-based, so I didn't want students to have to install anything. And the point wasn't really to replace completely GHC or GHCI. We still use it because I want them to make larger programs. I want them to see functional programming as something that they can build their exercises in and build future projects in. So here's an example of the sort of thing I want to build. So if the student writes that program and asks to evaluate that expression. So the program is an insertion into a list that's supposed to be ordered and maintaining the ordering. It will produce a step-by-step trace like this with the equations in between. So rather than do this, I'll just show you how it works. So I have this prepared, but this is an editor. The students can change anything, evaluate, and then go step by step until they reach the final result. Okay? You can also hide the justifications, and they will appear as sort of tooltips over there. So this is what I want to get. So how did we come to this? So this required a slightly new look at the way you do this evaluation. So a new core language based on a pattern matching calculus. The idea is to have explicit treatment of the nested patterns and failure. And the reason for this is that I want a close relation between what I am executing and what the student wrote. I don't want to have a huge semantic gap, a translation between the two. Then I developed a big step semantics based on the one of Launchbury, a small step semantics for the abstract machine, which is actually the thing that we do implement, because the big step semantics requires you to do the whole evaluation at once, and I want to do it piecewise. There's a correspondence between the two semantics, a sketch of the proof. It's not particularly difficult, but it's in the paper. And some extensions that I'm going to show you for bank patterns, for example, that allows us to show lazy evaluation at work. The implementation is freely available. You don't need to install anything. You can just test it on web. So but let's first start with this idea of why do I need a pattern matching calculus? So the standard technique in lazy functional languages for implementing pattern matching, nested patterns, overlapping patterns, is to translate them into simple cases like those. That's a function that's supposed to tell me if a list is short. So if it has at least 2 elements, it's not short, otherwise it is short. But the translation that something like GHC will do is do the thing on the right. There's a single equation, a case that takes apart a constructor and at one level only. So there's one constructor and variables, and then again, one constructor and variables, and you have to cover all the cases there. So why is this done? So the big advantage is that in a lazy language, you don't want to over-evaluate. So this way, you evaluate just as much as you need to make the next decision. So a simple case forces evaluation just to the outermost constructor. You don't need backtracking. You don't need any way of handling the failure except as a sort of panic or something like that. And in practice, it can be implemented very efficiently because it's almost like a machine-level switch. There's variable binding as well, but that's not particularly difficult. The disadvantage is that doing this translation isn't straightforward. I call it non-local in the sense that you have to have a global view of the equations in your program, and you have to be careful to avoid duplicating work. So there's a whole chapter of the classic implementation of functional language book dedicated to that. And the thing is that when you reach the final program, then the thing you're going to execute no longer relates to the original program. It's not easy to point out which equation was used at which point, and this gets even more complicated. You have things like guards or So what's the alternative? The alternative we employ is a pattern matching calculus. And this is how it's going to look in our pattern matching calculus that I'll show you in formal detail later. If you squint, it sort of looks like lambda case, but it's a little bit more general than lambda case for composition of the evaluation. So the idea is that you have nested patterns, you have a notion of alternative and a notion of failure, explicit failure in the calculus, and so the operational semantics actually does something closer to what the programmer wrote. And it's less efficient because you have to manage this alternative backtracking, but that's not a major concern in a tool where you're going to use it for small programs anyway. Okay, so this is what I'm going to go through. First, the syntax. So I call this Lambda PMC. The original work is called PMC. It's by Wolfram Kahl. And it's essentially the same thing except for some syntactic notation differences and adding a form of local bindings. So there are three syntactical categories. So we have expressions, as in the lambda calculus, as in core, but we also have matchings and patterns. So expressions are on the left, matchings on the right, patterns on the bottom. Expressions and patterns are mutually recursive. So expressions can contain matchings, and matchings can contain expressions. The patterns only occur inside matchings. They don't occur in expressions. So let's look at these in more detail. So the first few cases are just like the lambda calculus. There are variables, free variables. There's application. But then you don't have a lambda abstraction. You have a lambda which simply injects a matching as an expression. So it's taking a matching and treating it as an expression. A matching will represent functions, but not just functions. You could have sort of already fully applied functions as well. And you have constructors. And constructors, as in core and STG, are supposed to be saturated. So you don't under-apply a constructor. Then you have matchings, and matchings have a few cases. So the first case is the case where you already know the matching succeeded, and you're going to continue with some expression. That's the success. The second case is a failure, when you haven't matched your input. And the third is a function expecting a result that matches some pattern and continues with some matching. The third is a supply of an argument. So it's really just another form of application. So this is like application, but it's written in reverse order. So the argument is here in the E, and the matching is the continuation. So this is what allows us to be compositional. I'm not actually going to show you the matching rules here, they're in the paper, but we want to make this compositional. So define the semantics of matching by splitting apart the constructors and continuing matching smaller things. And this construct is what allows this. By the way, this syntax is from Kahl. And then we have alternatives, and we have a way of doing local bindings. Patterns are just variables or constructors with more patterns, so you can have nested patterns. So let's look at how this works for translating something like Haskell. So I'm not going to do a formal translation because I would need a formal definition of Haskell, and that's beyond the scope of this work. So the general idea is that the translation is quite straightforward to do. Multiple equations will correspond to a binding with a matching with multiple alternatives. If you have overlapping or nested patterns, you don't change them, you just leave them as they are. Case expressions, ifs, guards are all special cases of matchings. So here are some examples. Just as expression, a lambda, that really translates to lambda and then a matching with the same variables. So that's why I'm using this symbol for injecting a matching, because most of the cases this will be a function. But this is not a function. This is an expression with some free variables that supposedly are in context. It's still translated to an expression that looks like a matching. So it's lambda, and then here you have the argument that's been supplied to the alternatives. True will be this case, false will be that case, and you have to go back to expressions at the end. So this is a definition of binding. So this will be translated into a binding, but the right-hand side is always a single expression, including matching. In this case, there's no definition for the empty list, so it only includes this case. This one has two equations that they translate to two different branches in the matching. And this is the first example we saw. So here is a more complex example using guards. and has patterns as well. So here I have an equation that applies when the list has at least 2 elements. I named the sub-expression, the sublist there, and I also have a guard saying that they have to satisfy this predicate. So I have to do computation while doing matching. So this has to be something that has to be executed while doing the matching. And it turns out you can do these things by this interleaving between matchings and expressions. So there's a first argument, which is this outer pattern. Then you take the second argument and you match it against the sub-pattern. And then you match the guard against true. And if all of these things succeed, then you go on to the recursive call. The second case is the translation of this equation. It doesn't need to consider whether this happened or not, because the ordering here matters. The first case will be tried first, and the second. And the final case is the empty list. It's also possible to encode more sophisticated things like pattern guards and view patterns. That was already noted by Kahl in the original paper. By the way, this translation is also in the original paper. It's nothing new here. So what is new? One of the things is having the naming mechanism for sharing, something like a let binding. But I called it where instead of let. And why is that? Because we do need both, because we have 2 syntactic categories. We have expressions and matchings. And this is analogous to what happens in Haskell. You can use let for expressions and where for bindings. And where, for example, you can find names that scope over a guard, whereas with let, they will only scope over the right-hand side. So by analogy, what I used was where when I define the bindings in matchings. And it turns out that you don't actually need the let, because you can define the let by a simple translation into a where. So let will be a lambda with no argument that just has the expression where the bindings. So this way, I can just have one of them. Well, you could ask, why did I choose the where and not the let? Well, the let isn't so easy to use as a primitive for defining the where, because matchings can fail and expressions don't fail. When you get an expression, you can't go back and say, oh, that was not the case I wanted to treat. So I take where as a primitive and let is syntactic sugar. So now we're going to the semantics. So the idea is defining the simplest form of semantics that I can do to give an interpreter. And that's an operational semantics, a natural operational semantics, based on a Launchbury semantics. Actually, Sestoft's revision of Launchbury semantics. The first thing we have to realize is that it's very important not to duplicate work. So we have to work on normalized terms. This means arguments to applications, so the arguments to applications in expressions and applications in matchings, both of them need to be simple variables. I'm using y to mean that they are not bound, they're sort of free somewhere and not bound. The arguments of constructors themselves must be simple variables. And then we have a heap that captures these free variables around. A heap is simply a mapping from free variables to expressions. The expressions can be suspended, like funcs, or they can be reduced, already reduced. And these are used to memorize evaluations. And there are 2 mutually recursive judgments: evaluate expressions, evaluate matchings. So let's look at what this shape of the judgment looks. This is just like Launchbury semantics for expressions. So this is initial heap. This is a technical add-on, which is a list of things that are, a set of variables that are under evaluation. It's only required to define the notion of freshness. And then we have the expression, the final heap, and the result. And what is the result? It's a generalization of the notion of weak head normal form, typical of functional languages, lazy functional languages. So it's either a constructor with evaluated to the outermost form. So you know the outer constructor, but the inside are variables that can point to unevaluated things, or it's a lambda, but not any lambda. It has to be expecting at least one argument. If it is already saturated, then it's still not our normal form. We have to reduce it further. And this symbol means arity. It's defined in the paper. It's a simple syntactic measure over the term. And we have a matching an evaluation for matchings as well. And this is new because now the result isn't a weak head normal form. So we also need the heap. And we need the set of variables for the freshness condition. We need another argument, another stack, which is a stack of things that are being supplied to the matching. This is for compositionality when you go inside the patterns. You need the matching you're going to execute, and the final heap. So matching will possibly change the heap, because matching will provoke evaluation. So you can have further things being evaluated, and you have to record, memorize those results. So you have to get the heap in and the heap out. And what is the result? It's either a success expression, so this matching, or a failure. And both are defined in the paper. I'm not going to go over them here. So this is my specification, and this is designed to ensure that I believe this is doing a lazy evaluation. But to implement a step-by-step interpreter, I need something where I can stop the evaluation partway through. And that's really just turning that big step semantics into a small step semantics. And it looks like this. There's a state configuration, and each reduction is a change in the configuration. So there's a heap, there's a control, which is essentially which of the modes you're doing the evaluation, because you're going to be alternating between expressions and matchings. And there's a return stack, which is essentially the continuation. I call it a list of continuations, but technically, the whole thing is the continuation. And the paper has the transition rules. Okay, so this is the formal basis for the implementation. So, but there are still things to do. How is the implementation done? It's written in Elm, and it compiles to JavaScript, so the whole thing runs on your web browser. There's no server. You don't need to connect to anyone. You can copy the assets or clone it into your machine and have it running locally on your internal network. It implements a reasonable subset. So it implements more things than the model, the semantics, so things like integers, characters. You can define your own data types and define the constructors. Multiple equations, nested patterns, guards, cases, let where. A lot of the prelude functions are there, they're predefined. You can define them yourself, redefine them if you want to use a different version to show the different operational aspects. It does parsing using an Elm parser combinator library, does type checking and step-by-step evaluation. And there are some extensions that I'm going to show for bank patterns and forcing evaluation. By the way, this GitHub page has the actual demos. There's lots of demos you can try there. You can run it on a smartphone. It's fast enough to run on a smartphone, no problem there. So how does the parsing and type checking work? Pretty standard stuff. There's nothing very sophisticated here. I build an enriched AST just so that I allow better error messages, or I should actually say less bad error messages. We'll come to that. Type checking and inference is very simple. It's just Hindley-Milner. There are no type classes. There's monomorphic arithmetic. There's only one num type, which is int. There is a polymorphic equality, but it's implemented ad hoc as structural equality inside the interpreter that may fail if you supply, say, a function to it. No higher kinded types, just simplify kind inference. And the step-by-step evaluation, how is it done? So, we implement the abstract machine transitions almost exactly how they are in the paper, but there are some primitives for integers and characters. Those are not particularly difficult. How do we do normalization? We build special variables that we call indirections that can be detected and short-circuited during presentation. So this is what allows presenting the evaluation as if it was on expressions, even though it is graph reduction. So I don't want to show to the students the heap and pointers going around. I want to keep the illusion that you're doing term rewriting on strings or expressions, but actually have the lazy evaluation, because I want to do non-strict evaluation, and this is more efficient if I do it this way. There's still a problem, which is, if you look at the paper, I haven't shown you here, there are lots of rules, lots of configurations, and it's very technical, and I don't want to overload students with that. I mean, these are not PLT students. These are first-year students. I can't show them the Lambda PMC. They are starting with Haskell, so I can only show them things that look like Haskell. So what do? I want to avoid showing all transitions, just show some of them. And I come up with an heuristic that actually works really well, and it's very simple. you only show a configuration in two cases. After you've done a primitive, like after you've evaluated plus with 2 concrete integers, you get 3, that's shown. And after you've done a successful matching. So whenever you reach something that is like that matching with a return expression, you will show that to the students. And you pretty print it in a way that it looks like an expression. I never show things that are specific to the Lambda PMC. So how do I show? I mean, showing the primitives is easy because I can just pretty print them in the interpreter. But how do I show the equations? And the solution here is very low tech, but it works well, which is when you do the parsing, just annotate each of these return expressions with the program text that led to that part. So this is what it would look like for the initial example that I've shown you. So this is the original program, and this is actually what we do build inside our interpreter. And note that every of those return expressions has a string, and the string is taken from what the student wrote or what the programmer wrote. And the advantage here is that you get you don't have problems of having done some sort of desugaring or some sort of simplification that you then have to revert back when you're showing to the user. You just use whatever they chose as a way of writing the program. Yeah. So what else can this do? It's very easy to add some evaluation extensions. So bank patterns is one of them. That actually wasn't in Kahl's original calculus. I mean, Kahl's calculus was just a calculus. It just proved confluence. It didn't care about a reduction strategy. So the concept of strictness and doesn't really make sense in that setting. But it does in Haskell. And so we can use bank patterns and define fold L prime as well as fold L. And the difference, if you notice, is just this little annotation here. Whenever you take the accumulator in the recursive case, force it before continuing. And this allows us to show what a space leak is simply by term rewriting, simply by looking at expressions. The evaluation rules are simple and they're in the paper, but I'm going to show you what it looks like. So the left side is the lazy fold L. The right side is the strict fold L prime. And the operator we're using is times with a list of integers. And if you look at the lazy version, you can see that it's building up in the accumulator position this expression that mimics the original list. And at the end, you then get to reduce it all down to a number. So it's building up the expression and then reducing. And if you force the evaluation at this point, then what you get is that each step of the reduction, you force the evaluation of the accumulator and then continue with the accumulator forced. So you end up interleaving the work of computing the accumulator with the recursion, which is exactly what you want to avoid this space leak. So notice that the number of steps is exactly the same. So it's doing the same work, but it's distributing it differently. And I don't have to talk about thunks or look at core or look at STG. It just comes out of the rewriting. So there are more examples in the paper. For example, if you have a pair, you can show what happens if you have outer strictness but not strictness inside the pair. You still get the space leak. So it's all composes very well. Okay, so some related work. There's lots of work for teaching Haskell and teaching reductions. And so here are some interesting prior work. So HAT is a tracing tool for Haskell programs. It works by instrumenting your program. So you have to import the library, annotate it, compile, run it, and then use an external program to look at the traces and do something. It doesn't actually annotate the steps. It just shows how you call the function, so what arguments you use to call each function. And this whole annotate your program, compile, run, it's a much higher entry barrier. It's hard enough getting students to install GHC and then asking them to install an extra library and doing some annotation. It's a lot of syntactic overload, and I wanted to avoid all that. More recently, there's this Haskell expression evaluator, which is based on term rewriting. This is really based on term rewriting. It supports different strategies, so You could do outermost or innermost. I think not lazy evaluation, so we could do a call by name or outermost reduction, but not lazy evaluation. It can show the evaluations and check students' evaluations, but it is a tool that requires lecturers to provide some exercise, and then students can fill the exercise, but they can't put in their own definitions. And there's more related work in the paper. So, conclusion. So we have a lightweight step-by-step interpreter for a small subset of Haskell. It's not a new problem. I mean, most of the citations in this paper are quite old because of that. But what I want to point out is that there are different trade-offs that led to a different decision. In particular, I care more about how do I present the results to my students, how do I lower the barrier for experimenting with this evaluator. One thing that I learned when doing this is that lazy evaluation and pattern matching really are interact in subtle ways. Pattern matching is more subtle in lazy languages than it is in strict languages. For example, we really need interleaving between evaluating and matching. You can't split the two apart. And the other thing is the formal semantics really helped this implementation, because what I'm showing you is not the first version of this work. The first version was a bit of a hack, and I gave up on time and said, no, I teach this stuff. I should be able to do this on a more fundamental basis. So for further work, we're doing an educational assessment. So the last semester we taught functional programming using Haskelite. We asked students for feedback. Spoiler alert, a better error message is what every student asked for. Things we're not doing, bindings with patterns. You can't do let P, where P is a pattern, equals an expression. This is a bit subtle because the semantics there is that you should be lazy in the patterns. It's what the Haskell report calls the irrefutable patterns. So list comprehensions, we don't do that as well. The reason for not doing it is that we'd have to translate them to things like concat map with filter, but list comprehensions are usually introduced before higher order functions. So this would lead to a situation where the code that the students run doesn't look like what it wrote. Type classes, well, I'm not sure they should be put there. You could put them, but then you get the problem of dictionaries coming up around, and again, some artifact that the student didn't write appearing in the execution. IO and effects, same thing. So, and with this, I'm ready to take some questions.
The impression I get from the talk is that in this class that you're teaching, the meaning of a program can only be arrived at evaluating it in a very special way.
Yeah.
Do you teach in your class then? Or perhaps I can ask, how do you teach in your class then? Yeah. The concept of non-strict semantics.
Yeah. You're right. What you're saying is the interpreter is choosing one strategy, one particular strategy, whereas in many cases you could evaluate in a different order. And you could show to students that and what you get would be something like confluence. If it terminates, then you would still get the same answer. That's on a sort of possible extension, which is you could allow students to say, let's evaluate that bit first before continuing. That would no longer correspond to the Launchbury semantics, which has to pick one particular strategy, but it could be done because it's interactive. You could just force this little bit over there. And when we teach, we do say that, well, this is just like doing rewriting in mathematics. You can do it in any order you like. What Haskell does is do the least amount of work, so don't do work before it's actually needed to make a decision. Okay, I'm not sure if this answers your question, but...
I'm Farhad Mehta from the OST. This is really great work. I've been looking for something exactly like this. Thank you very much. My question is, I have actually two. So my first question is that, so this is not exactly Haskell, it's a subset, right? Yep. At what point do the students realize this, and does it really pain?
Yeah, I warned them right at the beginning. That's why I called it Haskelite, as a sense that it's a lighter version. it is a problem, because even though I've warned them in lectures, and I use it in lectures, that you don't have type classes, you don't do deriving show after, you can't use floats, for example. There's always some student that comes back to me with, well, why isn't this working? Yeah, the thing is, we're all programming language people. We're used to this notion of layers in languages and syntactic sugar and core and extensions. That's not a natural thing. I mean, students don't think of languages like that. So at one point, I think maybe it would actually be beneficial to accept more things in the parser and just give a message, a more directed message saying, in this interpreter, you can't actually use that, although that's suitable Haskell, for example. Yeah.
Yeah, cool. Thanks. Ah, okay. Can I ask that? Yeah. My second question is about this this pretty printing that you had. So you had the term and then the little string there, right? That's another thing that I was always failing with. When you just store the string, how do you need to actually manipulate the string depending on your manipulation of terms? How do you do this? You don't always have the same string hanging around.
Well, you just keep track of an attribute in the parser. Keep track of the lexeme that was consumed. In a parser combinator library, you can get access to whatever was consumed by a combinator. And then you can concatenate the thing.
And
it's
you
really
recursively just
copy-pasting. It's really nothing clever.
Got it. Thank you.